As you can see, the title is slightly different to what's written on the program. I will be talking about CDI today, but I also want to give a bit of background into why we sort of started focusing in on that technology in particular for the treatment of remote groundwaters. And it stemmed from a larger project looking at different treatment options for water supply options for remote communities in NT and WA. I'm presenting this work on behalf of my boss, David Waite, who unfortunately is overseas at the moment and couldn't make it. As I mentioned, it was part of a linkage project, and under that umbrella, the funding went through UNSW to the Water Research Centre, and also partly to the Centre for Membrane and Science Technology, so led by Professor David Waite and Greg Leslie. But in conjunction with our industry partners, primarily the Australian government, our primary partner was Beijing Origin Water, a large Chinese water tech company. And along with NT Power and Water, WA Water Corp and Water RA, it formed this unique and really nice blend of both innovation but also application. A very brief introduction about the driving force behind the research. Essentially, we're trying to address issues, I put them in the last point there, relating to retention of or rejection of contaminants, issues around fouling of membranes, poor reliability, cost issues associated with advanced treatment options in remote communities. So EDR, electrodialysis reversal, and RO, reverse osmosis principally. And in order to investigate that, we followed multiple different research avenues. I listed them up here. In the 15 minutes, I won't get across all of those, so I'll gloss over a few of the slides. But I will focus around the EDR RO comparisons and also the CDI, taking that from lab scale through to prototype. As I mentioned, Beijing Origin Water was our major funding partner on the project, and they wanted out of us some information about a new membrane that they developed as a way of point-of-use treatment for brackish waters. So it's certainly applicable to many Australian scenarios. And they were hoping it was going to sit somewhere in between RO and NF. And so we ran it through a series of filtration exercises, cross-flow, dead-end filtration, and compared it to well-established, well-characterised RO and NF membranes. It kind of behaved like an NF membrane with regards to nitrate retention, and even more poorly when it came to fluoride rejection. But the main point here was our ongoing collaboration with a big water tech company. We've worked with them previously on MBRs, and now, although they weren't the results that they were hoping to find with regards to the Dalton filtration, we've since continued to collaborate with them. This time we're looking to use CDI, so Capacitive Deionisation, for resource recovery, and I'll get to that in a later slide. So we know that EDR and RO are the two primary treatment options when it comes to contaminated waters required for drinking water in NT and WA. So these are the two that we focused on primarily in our research. We have facilities to test RO previously, but didn't for EDR. So we built a pilot scale or a lab scale unit. You can see down the bottom right there the stack of ion exchange membranes, and on the right is the piloting equipment and the plumbing. And because we built it from scratch, it enabled us to have complete flexibility over what we wanted to test and how we could test it, and the parameters that we could use. And so that was really key to our understanding. In this case, we were just looking at nitrate removal, something easy to measure. And the results are pretty unsurprising. EDR didn't remove as much nitrate compared to RO. So that wasn't really the key of the work. It was more, which is the bottom four graphs, understanding how the work can be applied to specific communities. And so therefore NT groundwater sourced remote communities. But those graphs show the EDR comparison with RO when you factor in the power consumption per percent of nitrate removed. And that's where EDR starts to come into its own once that energy consumption issue is factored in. And I guess this slide is put up just to highlight how we can specifically tailor treatment options for specific waters for different communities. And we did that right across, I think, about 72 communities in WA and NT, comparing RO and EDR. And the example on the right just gives a rough cost breakdown of your typical treatment plant, 225 kilolitres per day, and where those costs go. But generally speaking, across all communities, the primary factors influencing cost were the technological approach, water service level target, feed water quality, and the population density. We also did some further work on costing analysis, this time resilience modelling, where we look to manage the assets of EDR and RO more effectively. Without going into the details of the method, essentially it draws upon historical data from water treatment plants and their susceptibility to failure and the reasons for those failure. And then we perform a sensitivity analysis on some key scenarios that we impose on the system. And we assess that sensitivity based on two key outcomes: quantity, so the amount of plant downtime, and quality, so what happens to the water quality during those downtime periods. Is it compromised? And the two scenarios that we put into this model were, one, more efficient maintenance protocols, so having reduced mean downtime, and number two was adding extra standby units for components that were pre-existingly known to fail prematurely. The graphs generated a lot of data. The graphs down the bottom are just a couple of examples. The one on the left, the quantity, the downtime, and the quality, the water quality. And you can see that scenario one, in comparison to baseline, had significant improvements on both the quantity and quality issues, which is kind of unsurprising if you have more efficient maintenance protocols. Perhaps more interesting is scenario two. EDR certainly benefited by having more standby units compared to RO, significantly more than RO. This is going to be one slide I'll gloss over. We had an honours student who was interested in looking at whether EDR brine could be used to regenerate ion exchange resins as an alternative to, say, acid dosing for scale treatment in EDRs. He based it on the 1 to 100 scale model of the Uluru EDR plants. And although the cost that's just cut off there was, the cost benefit worked out slightly positive, it was marginal. We could never reach the 5,000 milligrams per litre of sodium required to fully regenerate that IX resin. And so additional sodium chloride would need to be brought in. So it's not an avenue we're actively pursuing at this stage unless some breakthrough can be made. We also do a lot of work in membrane fouling and cleaning. This stems from the previous work that we've done with regards to MBRs. Our particular focus is iron and understanding how the structure of that fouling layer has the potential to affect water retention, and also developing novel ways, so using complexants and reducing agents to clean the membranes as well. There's some lists of publications at the end of my talk if you want to read more about any of these topics. Okay, so to CDI. So this water treatment technology has made quite rapid advance in the last, say, 10 years. For those who might not be familiar, it uses an electrical potential, usually across two porous carbon electrodes, that first diagram there. Thanks, Wikipedia, for something nice and simple. Once the potential is applied, the ions migrate to their respective electrodes and are stored in the electrical double layer until you switch off the potential, or indeed reverse it, and then it kicks it back into the brine phase and it goes to waste. It's frequently described as a robust, energy efficient and potentially cost-effective method for low to moderate salinity groundwaters. And that's because you need relatively little voltage to achieve good separation, and so it does make it quite amenable for photovoltaic-driven units to be manufactured. again, we decided just to make our own, to give us full control over the experiments. And we also complemented that and ground truth that with off-the-shelf units as well. Another good thing about CDI is it can be scaled right down, unlike EDR, for example. So off-the-shelf units are quite cost-effective. And so that enabled us to do a whole lot of different experiments. I won't go into them. Our primary focus was to look at contaminant removal from waters. And we started off initially just looking at fluoride and nitrate, primarily fluoride. And that's some data from the first publication that the group did on CDI. Waters from 500 parts per million up to 3,000, and you're still getting reasonable removal of fluoride and nitrate. So it certainly caught our interest in terms of a technology that we wanted to continue with. And this has then evolved into a whole range of different studies, mostly around optimising contaminant removal based on the different configurations of CDI. So I've listed a few there. And again, the publications are probably the best source of information at this stage. And the other cool thing about CDI is the potential for energy recovery. So during the desorption stays, the system works as a capacitor, and if we can recover that energy, which our second generation cells are now recovering up to 60%, and through some novel power designs, cell designs and power board manipulation, reducing heat outputs, we can really reduce our cost per kilolitre. So stepping back from the fundamental research, we can really see where this technology can be applied. And the obvious one is treatment of low to moderate saline groundwaters for drinking water treatments. And to that end, we've engaged with Tata Corporation. They're a big Indian company you've probably heard of, who are quite committed to providing clean drinking water for a lot of the Indian population. And they've commissioned us to build a full prototype, which is that one up the top right. It's purely PV powered, a kilolitre an hour, and a constant current CDI. It's about to be trialled in Western India, in Karnataka state. Where do we see the applications for CDI? We think there's big scope for it to be used for the treatment of brackish groundwaters in agricultural development in regional Australia. We've actually got a student just started on working on that, and also the targeted recovery of elements such as lithium, which is the project with Origin Water, but also phosphorus and uranium. I won't go over the summary because I've probably said everything already, but these are the publications for CDI membrane fouling cleaning if you're interested in reading more, and the student theses that came out of the linkage project. Thanks very much for your time.
Thank you, Andrew. We've probably got time for one quick question if anyone's first up.
So with your EDR,
yes.